This is a short presentation about the book that I have recently finished writing. The book is about programming in System F Omega using Dhall. You can get this book on LeanPub. If you want a paper version, go to lulu.com and search for my name or for the title of this book, and you can pay a grossly inflated price for the paper version, but that's what you have to pay today for such print on demand. However, you can read it for free. It's an open source book in Markdown. The entire source code, entire source text, and the source code is here in this repository as part of my Scala-based implementation of Dhall. So not as nice formatted as the PDF, but you can get the entire material if you feel like. So what is the vision for this book and why did I write it? The main motivation was my interest for the Dhall language. The Dhall language was positioned as a programmable configuration language. In other words, you would like to replace all this difficult to use templating languages for JSON and YAML by a strongly typed, statically typed functional language that allows you to perform validations statically before you export your JSON or YAML configuration. For me, however, most interesting is that this is a purely functional and very powerful language, although it's a very small, easy to learn language. And the reason why it is so powerful is because it is essentially a flavor of lambda calculus, which is called System F Omega. This is how you would write some code in that language. And you see it's a lambda calculus in a syntax that looks like this, which is fairly readable. And let's see, you can apply this lambda function to some expression. And the normalized form of this expression is the literal natural number 31. So you see, this is what the programming in lambda calculus looks like. You write an expression, everything is just an expression, and you get the final normal form of that expression, which is the evaluated result that you would like. So System F Omega is at the foundation of programming languages such as Haskell, Scala, and others, PureScript, as well as Idris, Agda, Lean, and other proof-assistant languages. Certainly these languages have more features than System F Omega. System F Omega is the basic lambda calculus that you can just imagine that it's lambda calculus with types, with static types, also with type constructors. Functions can have type parameters, but also with higher-kinded types. In other words, the type parameters themselves could be type constructors. So that is the power that this little language has. So because here I could say lambda with a different type annotation, and right away I have the entire power of System F Omega at my fingertips. So in my view, certainly it is very useful to have a templating system that replaces the jumble of templating languages for JSON and YAML. But my interest for this book is to explore the kind of programming that you get if you start working with this sort of lambda calculus. So it is a very different kind of lambda calculus than what you would read say in Wikipedia when you look for lambda calculus. because they're static types and all these features of the type system, especially higher kinded types, which make programming a very different experience in this lambda calculus, in the system F omega. So this is indeed an exploration of this sort of programming paradigm where you have functional programming, which is pure, there are no side effects at all, and also there is guaranteed termination. The guaranteed termination comes from the fact that there is no recursion. Pure lambda calculus does not have recursion, and in untyped lambda calculus you could implement something called the Y combinator and other recursion combinators, which you cannot implement in typed lambda calculus. And so in this lambda calculus, for example, you have syntax like this. Right, so you can introduce what looks like variables, but actually this does not allow you to have recursion, because you cannot say let f equals f plus 1 or something like this. This is not allowed because f cannot be used on the right hand side of its own definition. The error message is unbound variable f, which is here. It is unbound here. If I say here y, it's the same error. Unbound variable f. So f is not defined, and I cannot have a definition that uses f itself because of this. So I cannot have a recursive definition. I cannot define recursive functions. I cannot define recursive types directly in this statically typed lambda calculus. The advantage that it gives you is that everything is terminating. You cannot have unterminating recursion or infinite loops. The downside, of course, is that you need tricks to encode any sort of recursive algorithms, which you can do. You can absolutely encode recursive types and recursive functions, such as what you would like in functional programming. The recursive types, such as lists and trees, and recursive functions on them, such as loops and folds and filter and map and so on. You would like to program with your recursive types and data structures using those methods, and you can do that. However, it requires certain tricks, and these tricks are explained in the book. So the main tool for encoding recursive types is called the church encoding. This is a major part of the material in this book, that is explaining and exploring the church encoding and how to use it in practice. If you look, as I would say, in Wikipedia or elsewhere for information about church encoding, you will see very little useful information. You will see that church encoding looks like just some tricks that are really not relevant today to anything. Tricks for encoding integers or natural numbers in untyped lambda calculus, or encoding pairs in untyped lambda calculus. Now, this doesn't do a great service to what church encoding could be, because when you are working in a statically typed language with type constructors and higher kinded types, church encoding becomes much more powerful. It becomes a powerful means of encoding any sort of recursive data type, or even dependent types, GADTs, existential types, and all sorts of things that are useful in advanced functional programming. And yet you can encode all of this without having these features in the language. So the Dhall language, or the system of omega, does not have GADTs as a feature, does not have existential types as a feature, it does not have even recursive types, it does not have say dependent pairs or something like this as a feature, but you can encode it using church encoding. You can even encode Leibniz equality, which is a dependently typed equality type for values and for types. So all of this can be done. I explain this in some detail as well, although Leibniz equality does not occupy a huge place in this book. Dhall language has a feature where you can say, I want to assert that x is equal to 123, and that assertion will be checked, and if I have a wrong number here, then the entire program will fail to type check. So this feature is good enough to cover most use cases that you would need for equality types used for different assertions. You can assert that certain parts of your configuration file have certain properties, and that's in most cases good enough for practice. So in this book I just show how to define more general equality types, and I show how to define church encodings in general, the most general form of church encodings. Explain all of this in detail, and explain, for instance, why we can have recursive types and recursive functions even though none of the code we write is actually recursive. So I explain this all in detail. I also talk about other practical matters regarding the programming paradigm in the system of omega, what the experience is like. For instance, can you have partial functions really or not? Because what is there a strict or lazy evaluation or not? I also talk a little bit about this problem of size explosion, and this is a problem that is unfamiliar to most programmers used to programming in other languages, where normal forms is not the main means of evaluation. In Dhall, normal forms is the only thing that is being evaluated, because everything is just a big expression. And this expression could be itself a lambda. So let me write an example. So now the normal form of this is this lambda. And I can put m in here, for example. And as you can see, Dhall will simplify as much as possible. It will substitute where it can. I can put m also here, right? Now you see it does not simplify algebraically. This expression could be simplified more, but Dhall does not include evaluator or simplifier for numbers or for other theories. It's just a more basic evaluator. So this is a normal form for Dhall. Now you see it does simplify a little bit under lambda. So if I, for example, if I do this, let me try this. Right. So you see it tries to simplify, but it cannot always simplify to the most shortest possible form. And The result of this, so to speak, normal form-oriented programming, where the final result is always simplified as much as possible, but not more than possible, is that you have explicit lambdas that could become quite long, especially if you're writing a library of functions that you want to use later. So, and Dhall allows you to do that. It has a very simple module system where you can write functions in different modules and then import those functions later and use them. And the result, if you do that sometimes, is that even short code like this, it's a very seemingly short code, actually has a very large normal form. The normal form of this h here, after all substitutions, is about 800 kilobytes of lambdas, essentially, different kinds of lambdas all over. And different function applications, and all of these are built-in functions in Dhall. So there are some lambdas that are built in. So this kind of code is extremely repetitive, and Dhall cannot simplify it really, because this is just applying functions to unknown parameters. So you don't know how to simplify this if L and K are unknown function parameters, and so which they are here. So this is a lambda with 4 parameters, and so they stay unevaluated like this. And this is a problem because sometimes the normal forms become very, very long, and it becomes very slow to work with them. It takes a lot of memory, time, and could even crash the system if the normal forms become too large. So this is an interesting feature of this normal form-oriented programming that is unusual, and I spent some time talking about it. And I hope that the future evolution of the Dhall language will fix this problem to some extent. And there are some discussions about how to do that. So in this book, I give a very detailed overview of all the features that system F omega has and Dhall has, and how to program with them. So I show how to implement, for instance, function combinators like function composition. I also show how to implement numerical algorithms like square root or division, logarithm, and so on, as it's not very obvious how you do this in a language that doesn't have recursion. Well, it turns out that it's not a problem that you don't have recursion. You have enough features. If you have a language with functions as a first-class values and type parameters, you have enough features to do everything you want. You can have, for instance, I implemented floating point operations where I have arbitrary precision floats, and I can compute square root, or even I can compute arbitrary number of digits of the number pi if I want to. Certainly not a very efficient way, but this is not a question of efficiency. Here is a question of principle and how you organize the computations in this system F omega. Then I talk about how to implement type classes, explain different type classes, and then the story really begins. Today's functional programming is not just functions that you apply to other functions. Today's functional programming is heavily based on types, and one of the most important features of type-oriented programming is type classes. Type classes can be implemented in system F omega. Certainly it is not very ergonomic, it is not very short to write code, but you can write exactly the same kind of code as you write except that, as you write in Scala or Haskell, in languages that have type classes, except that the type class evidence are explicit values. So I will just show you an example of what you would have to write. So you need to say this is a type parameter which is itself a type constructor, functions from type to type, and this is an argument which is an evidence that this f is pointed, and this is an argument that is evidence that f is a functor. So type class evidence is passed explicitly as arguments to functions, and this is how you implement type classes. I show how to implement the church encoding in all kinds of different situations, in many examples of lists, trees, non-empty lists, empty or non-empty trees, and so on. I also talk about higher kinded church encoding, because that's also necessary for certain situations, especially how to encode GADTs, generalized algebraic data types. So I show a Haskell example where you use a GADT to implement a domain-specific language, which is type safe, and I translate that into Dhall using church encoding of GADTs. So this is the church encoding of GADTs. You see there are lots of lambdas all over the place, but essentially it's very similar to what you would write in Haskell, except for a lot more code. However, all this code is more or less mechanical, and you could imagine tooling that will just write this code for you, some kind of autocomplete. And I show how to evaluate this domain-specific language using this GADT. So certainly working with church encodings is harder than working with recursive types that are defined directly in a programming language, but it can be done. I also show how to encode greatest fixed points. So least fixed points and greatest fixed points are recursive types, and least fixed points are usually polynomial recursive types. That is, they're data containers. They're like lists and trees, finite lists and finite trees. But you can also have infinite lists and infinite trees and other structures, like for example an infinite sequence, just an infinite sequence. There's always infinitely many numbers, and you can define that in System F Omega using a church encoding, and the church encoding gives you an existential quantifier which we define, and then you can work with it. So I show on many examples how you work with that. So one word about how this book uses Dhall for the code examples. The entire book can be seen as one big literal Dhall document. Literate, not literal, literate Dhall document. So literate programming means that you have text and you have code examples, and when you remove all the text and keep just all the code examples, then you can compile that. That's the idea of literate programming. So that means, for instance, if I define this somewhere in the book, then I can use it later in code examples in the book. And because the entire set of code examples is extracted from the book and compiled together, this works. So I can define here, for example, make G fix. I use it here, although I have defined it here. I use it later in the book. So whatever I define earlier in the book using the let expression, then I can use it later in the book. Now certainly some parts of code are not part of this literate evaluation. And for example, this is incomplete. This code is not really executable. It's illustrative only. So those are excluded from the evaluation. The incomplete things that can't compile, they are not part of the evaluation. Everything else is part of the evaluation, and it means that there are no mistakes here. In terms of types, all the assertions hold. So when I say assert, this actually tests the code, and all the code in the book is tested in this way throughout the entire book. The code is about 1/3 of the text of the book. So I show many examples of how to translate recursive functions, and that again seems to be a non-trivial piece of work that requires something called hylomorphisms, and hylomorphisms are not very well known, and also hylomorphisms actually have to be modified for system f omega because they have to guarantee termination, so they have to be bounded in terms of the number of iterations. So the basic idea of how you guarantee termination is that you do not allow arbitrary iteration. You allow iteration only when you know in advance how many, at most, iterations you will have. And that's fine. In most cases, you have that kind of upper bound, and then everything is fine. But you have to put that bound explicitly into your code, and I show in the examples how to do it. So for example, I show how to translate this naive Fibonacci code, which has even non-tail recursion, and so on. You can still translate that straightforwardly into system f omega. And for that, I showcase the so-called HIT algorithm. The HIT stands for the three authors, Hu, Iwasaki, and Takeichi. They have explained in a series of papers how to convert many sorts of recursive functions into hylomorphisms, and hylomorphisms then can be depth bounded, and that opens a way of converting a large range of recursive code into system f omega, even though system f omega does not have any recursion at all. So this is a very interesting pathway where you convert recursive algorithms into what looks like completely non-recursive code. So I talk about this for a while. For another example is Egyptian division, which is a very interesting example for me, because division in Dhall is not a built-in function, and so you have to implement it, and for large numbers it becomes slow, so you want a fast division algorithm. And I use that in my sample code for the pi, the digits of pi. So at this point the book goes into a large amount of examples that implement combinators for type classes. So like as I said, functional programming today is type class oriented, combinator oriented, and a large part of what is in this book is explaining how you combine different type classes, different members of type classes into new members. So if you have evidence that some types have belong to a type class, how do you construct a larger type that also has an evidence of belonging to a type class? And this is something that I explored in my other book, The Science of Functional Programming, in great length. How to find out, for example, what kind of types can be monoids. If you have some type t, then the function t to t, that type is a monoid. Or if you have p and q that are monoids, then the pair pq is a monoid. either PQ is a monoid. So these are what I call combinators. So if you combine types in some way, then can you derive type class evidence for the compound type from type class evidence of the constituent types? And this occupies a large part of the book. I show combinators for monoids, functors, contravariant functors, filterable functors, applicative functors, and applicative contrafunctors, monads, foldable, traversable. So this occupies a significant part of the book, and this is interesting because, first of all, it is not often shown how to do this, how you define, say, a monad, which is a product of two given monads. Or can you define that at all? Or can you define a coproduct of two monads, and when? So what if you have a recursive type? What if you have a type with existential quantifier? When can that be defined as a functor or applicative or filterable or something like this? So I explore this systematically and then show how to do with greatest fixed points, with least fixed points, everything. So there are type constructions in system F omega, which are unit type, void type, unit types, products, coproducts, function types. Then there are also constant identity functors, but these are kind of fixed types. And then universal quantifiers, existential quantifiers, and recursive construction, which is least fixed point and greatest fixed point. All of those type constructions can be implemented in system F omega, and I explore systematically what happens to types when you combine them using these type constructions. So this goes on. Let me go to the PDF version and show you what it looks like in terms of its table of contents. So these are the initial chapters showing an overview, then it goes into church encoding, and then all these combinators. Monad transformers can be implemented as well. Sometimes it becomes tricky how to implement correctly, since you don't have recursion, so you need to do everything using church encoding. For those who know about catamorphisms, essentially you are forced to do everything as a catamorphism. The only thing you have for your type is a catamorphism. You need to express all calculations using that. You cannot write arbitrary pattern matching with recursion as you are maybe used to doing. So this is what I've done, and you can do this. It turns out you can do this. You can implement all sorts of non-empty binary tree or non-empty list, non-empty stream, possibly empty binary tree, all kinds of things you can implement. And finally, I talk about free type class instances. So this is also an interesting topic which I explore here, how to do free functor, free monad, free applicative functor, free this and free that. So this actually occupies a large portion of the book, this kind of exploration. So there are some appendices that add some other interesting information that you might look at. So the first appendix is actually telling you how to derive a functional language from first principles. So what does it mean? Now, there are some principles of functional programming that I show here, and these are that every program is just a large expression, and the large expression must be built up by combining smaller expressions, and any part of anything must be changeable, or if it is changeable, then it must be an expression, and it can be replaced by another expression. So you should be able to change expressions, in particular you should be able to have a function that replaces some sub-expression by a given parameter, and then you can refactor any expression into a function where some part is replaceable. This is a principle, so your language must support that. And finally, every expression needs to have a certain fixed type, so the type must be known before evaluating the expression. And you need to reject expressions whose types you have determined to have a mismatch of any kind. So types must always match. And if you just go through and see where these principles lead, essentially you come up with system f omega. Dhall has more features than just pure functions. Dhall has records, union types, and some other features. But these features can be encoded using church encoding, which I believe I show here as well when I say church encoding of more complicated types. So church encodings can encode pretty much everything. I think I encoded here. I showed it here. So you can encode void type, unit types, product types, school product types using just functions, and you can encode recursive types and you can encode existential types. So what you need is functions and you need the universal quantifier. In other words, type parameters. You need functions with type parameters. Once you have that as a first class in your language, you're done. You have everything. And it follows that you have it, you cannot hide from it. So you have these features, and why not use them? And why not explore where that leads? What can you implement with them? That's the vision of the book. The second appendix is naturality and parametricity. Now, naturality and parametricity is a theoretical part of this book. Here I show some proofs. I actually show laws, naturality laws. I explain at some level the parametricity theorem. I do not prove it here, but I explain what it gives, what kind of laws it gives. I explain what is called a strong dinaturality law, which is a very powerful trick that you can use for proving properties of functions of this sort of type. So this is certainly not arbitrarily complicated sort of function type, where actually f, g, and h must be covariant, so they must be functors. So this is a certain sort of type which is often seen in church encoding, and the parametricity theorem gives you a certain equation that this satisfies, or rather relational property, which then is converted into equations, and that is what I explained here, how that works, and how to write that law. Now, this law is certainly not easy to understand, but this is as complicated as it gets for this book. So this much is that law. I explain in detail how that works, and using that law I prove everything else. I prove the Oneida identities, I prove the properties of church encoding, of least fixed points, of greatest fixed points. I prove properties of existential types that I need for other proofs. Also, I prove something called the church Oneida identity, which is not well known but extremely useful in this sort of setting for system f omega programming. The church Oneida identity and also the church co-Oneida identity, they are a generalization of both the church encoding and the Oneida identities in one type equivalence. So, for example, a functor applied to a greatest fixed point of another functor is encoded like this using existential type, and a functor applied to a least fixed point of another functor is encoded like this, which is similar to church encoding but a little more general. So this is a very useful theorem, the church unit identity as well as the church co-unit identity. I use it to prove several other things in this book. Curious little facts that I need for other proofs, which are actually interesting on their own, perhaps. How to prove, for example, the church encoding for mutually recursive types, how to prove the unrolling lemma, and there is something called nested fixed point lemma as well. In any case, I have an overview of everything that is being proved in this appendix, which is used in other parts of the book, but certainly the proofs themselves are just in the appendix because they're not so important to understand everything else. You can just skip the proofs. However, I wrote them down because I don't think they're written down anywhere in full. You cannot find them in any literature, any papers, any books, anywhere. Any tutorials. Nobody writes this out in full detail. Like, how do you prove that these formulas or these types are actually solutions of these fixed point equations giving the least fixed points? Nobody proves that anywhere, as far as I know. So this is what this book is. It certainly is a very interesting exercise for me, has been to go through all these implementations and to understand how to encode different constructions of advanced functional programming using system F omega. To me, this actually gave me more understanding, more intuition about those things, about, well, like, what is the higher kind of type? What is the generalized algebraic data type? It turns out, for example, that for certain data types, you need more lambdas than for others. Or for certain data types, you need a higher kinded church encoding. What's a higher kinded church encoding is when you have an arbitrary type constructor and also an arbitrary type quantified inside. So it's a very complicated type expression. So if you have an intuition to say you need to use this if you want to encode in system of omega a certain thing, and you cannot encode it in an easier or simpler way, it gives you an intuition that you're working with a very complicated construction. And GADT is one such example. And another interesting example that I found is the free applicative functor. So I went through all the free type class instances, and most of them are reasonably simple, except for the free applicative functor. That's very complicated. It requires GADTs, existential types, it requires higher kind of church encoding, everything. So actually, the free applicative functor, it looks really, really complicated. Like if you write it like that, that's what it looks like. And the code for it is pretty big. So this kind of intuition tells you that certain things are simpler than others, objectively simpler. A free functor is essentially that. It's not a big deal. Functor P. This is the free functor. Free monad is actually simpler than the free functor. It's actually, or is it? Yeah, well, this is a definition of the monad pattern functor that you need. It's actually not so complicated to implement the free monad. That's entire implementation. So this is an intuition that I got after writing this book, that certain things are simpler because they have a simpler encoding in system of omega. And system of omega is kind of a gold standard of the type systems of today's functional programming. Well, let me conclude now. So let me know what you think about this book. I'll give links in the description.